here. Wolfgang Stammer, giving a little lecture or a guest lecture here for us. Wolfgang is a postdoc in Darmstadt. He did also his PhD with Stan Kersting in Darmstadt, and he works on such interesting things like performative AI models that actually allow for introspection of the models and the decision-making process. And yeah, without any further ado, please, Wolfgang.
Thank you. People online, can you hear us?
There's no people online.
There's no people. Your power.
It's just
okay. All right. Then hello, I am Wolfgang. It's very exciting to be here. This is the first time I'm doing a lecture, so bear with me. I probably have way too much slides. You might have to rush through a bit, but I'll try to take breaks, especially because this is after lunch. Just very high level, my research interest is in how can we develop high-performing AI models that enable human users to understand and revise decision processes, for example, to mitigate shortcut behavior. Now, some of these topics we'll go into in the slides. And generally, one of the goals of my research is often how can we use symbolic, inherent concept representations to solve this question. So if anyone's interested afterwards, we can talk. So I don't know how much what you've done so far. So I have a longer motivation just because I always thought it was important as a student to understand why are we interested in this? Why is this important? So neural networks, as you know, are successful in many ways, and they are very successful due to one or several ingredients. One of them is using distributed representations, which means that information is stored within units or activations of the network. However, when you try to now understand the decision process of this neural network, as you probably all know in this class, it's very difficult. So if you want to understand what's the difference between why a model thinks an input shows an apple versus an orange, it's basically impossible within this embedding space, within this distributed representation, to understand what's going on. Now, why is this, from my perspective, very dangerous? Now, of course, generally humans like explanations, but if models work 100% correct, maybe many people would say we don't need explanations, but models don't work 100% correct, and I don't think they ever will, because similar to humans, they focus on, or they can focus on shortcut correlations or shortcut effects, which means that they focus on correlations which they found in a training data set, which they can use during training to solve the underlying task, for example, to classify images into horses or non-horses. But at test time, when these correlations are not present anymore, let's say they were a bug during the data curation, then these models would fail. Now, if you don't understand what the model is doing, you might not even be able to identify that the model is doing something wrong. And this effect of shortcut behavior has been found across various data sets by now, specifically focusing here on images. So from these kind of, quite simple horse classification images to medical applications, to even scientific applications where a model would focus on the background of a plant tissue rather than the plant tissue itself. Now, how can explanations, and then I'll go to how can concept explanations help here? So this example I just showed, this is actually what I started my PhD with. It was a very realistic situation. We had a project with plant biologists, and we got these huge amounts of data. We were supposed to, magically be able to predict when a plant is diseased or not, because the plant biologists in these huge hyperspectral cubes could not identify it. What we did was we trained back then, CNN on the data, and we had almost 100% performance, which of course the biologists said, wait, this can't be. This is just way too good. So they were wondering, okay, why is this model so good? What is it actually focusing on? And so what we did was we then applied importance map explanations onto this data, identifying where is the model looking at within the data set to make its predictions. And what we found was that the model for the disease class labels or the disease class samples would often focus on the liquid that the plants are embedded in rather than the plant tissue itself. Now, the question is, what do we do now with this? Can we just, we have to retrain the model, or another thing is we actually use the explanations not just as a one-way communication, but a two-way communication, such that the user can give feedback on the explanation and in that way revise the model. Similar to how essentially also we humans discuss, a communication is not just a one-way process, but a two-way process. And this process is called, or what we call it, the explanatory interactive learning framework. Interactive because it has a human in the loop. It's quite simple, or there are different ways of doing this, but usually you just have a additional regularization on the explanation of the model. So you have your basic prediction loss, LPRED, maybe a cross entropy loss, and now you add an additional loss. In this case, you mask or you receive masks from the human user, which would indicate with 0, 1, in these regions, you should not be focusing your attention or your explanation. In these regions, you should. And then you multiply that with the explanation of the model and penalize it such that finally, hopefully, via this guidance, the model will actually produce an explanation, which is excluding the regions the human user has specified. Another more simple approach would actually just to add additional data samples to your data set, specifically targeting these, let's say these correlations, if you've identified them, to just remove them, maybe, put white noise on them such that the model would not be able to focus on them during training. Now, in this example, we used input level explanations. They're often also called importance map explanations. They just tell you in the input, which part of the input is the model focusing on, yes or no. Now, most of my research is on concept explanations. Why? Because these input level explanations are actually pretty fuzzy. And in many cases, they don't really tell you much about the model. So let's say you have this image, it is classified as positive, whatever that means. Now, the question is it positive because the model is focusing on red, or because it's focusing on car, or it's focusing on a sporty car? We don't really know. And this kind of highlights this issue that input level explanations are ambiguous. They cannot tell you much about what the model's actually, let's say, thinking. And at the same time, there are other studies identifying in human user interactions, or human-human interactions, humans focus a lot more on high-level explanations, so-called kind of concepts to discuss. So one more thing, I think this is important to drive the point home. Is that what you say it? Let's stick with that. So let's say you have a simple data set. And again, we're focusing here on spurious correlations, or often called confounders. During training, these digits are all mapped to one specific color. So a model at training time can focus much more easily on the color than the actual shapes of the digits. At test time, we remove the color correlation, so it's completely mixed and random. And then what we would see is that the model performs very badly at test time. Now, if we use input level explanations, we would get something like this, identifying that, okay, the model is focusing on the digit, but somehow the prediction is wrong. And essentially without having access to the kind of these internal concept representations of the model, we cannot give feedback to the model in terms of XIL, so in explanatory feedback, to revise the model, because the model is focusing on the right part of the image, just for the wrong conceptual reasons here. So the goal is, and I think much of machine learning research is actually converging towards this as well, is that we actually want to explain and interact with humans and models via concept level explanations. So the big question is, how do we achieve these concept level explanations? How do we interact with these? Before I go into any of that, I think we should discuss what are concepts, because this is a very abstract term. Many people use it differently. The definition I have here, because everyone has different definitions as well, is very abstract as well. But bear with me. So in my terms, a concept means a mental representation or a cognitive construct that encapsulates the essential features or characteristics of a category. Now, in terms of AI models, concepts can be encoded implicitly within the weights of a model. So, the model has learned some kind of features, but we don't really know what. Or they can be encoded explicitly, so represented as concrete symbolic structures, maybe feature vectors, or concept embeddings. So concepts, they can be concrete versus abstract. They usually refer to some, semi-categorical ideas. And they can range from simple atomic logic to very complex logic, saying, this object has this property X, or, because we have this constraint and this constraint, but not this constraint, that can also be a concept. Questions so far? No. Maybe I'm going too fast, Evan. So in the next minutes, hour, I'll be going through several ideas from concept-based literature. We'll be focusing first on so-called post-hoc concept explanations. Now, I'm sure you've heard post-hoc as a term, right? Yes? Okay. So the idea of post-hoc concept-based explanations is quite simple. So you've trained a model to learn specific representations, and the model does something, but now you want to understand, okay, what in the model's embedding space is actually there. So you try to figure out what these concepts are, and then also how these concepts actually impact the model. So let's say we have a model which maps an input image X to a embedding H. Again, this is just the distributed representation, so the latent embedding. Now we want to map H to concepts like ball or cube. So very concrete kind of semantic information. A very classical idea, and this is actually pretty old, but I think it's important to know about, is just to probe for concepts. So let's say you already know what concepts you're looking for in advance. What you can do is you can curate a data set, have a second model basically try to identify those concepts from your curated data set from the latent embedding from your opaque black box model. And in this way, you can identify if the concept is present, to what degree. And now the next question is, okay, so we've identified it, but what can we do with this? Can we actually use it to test how much the model is actually focusing on these concepts, or if it's even using it? And this is the idea of so-called TCABs. Also, I mean, quite simple in the high-level idea. So again, you collect this data set. Let's say you have red objects versus not red objects. Now you want to identify, has your model, learned something like red or not red. So you train a binary classifier per concept to distinguish between red and not red on these embeddings of the black box model when you pass through the curated data set. Now, the learned weights of your binary classifier actually tells you the direction of red objects within the original model's latent space. Now you can use this basically direction to steer the model in specific ways and see if you actually, if you steer it in the direction of red, let's say, the model actually changes its prediction or not. And this way you can kind of probe the model further via this testing aspect. So, I'll focus only briefly on post-hoc in this presentation, but just now using TCABs as a kind of, how do you say it, an example of post-hoc explanations. Kind of a quick summary. So the advantage of post-hoc explanations, as you all know, but also post-hoc concept explanations, is that they're moderately easy to implement. You have the model, you don't have to change the model much, you add something on top. It can provide information about concept relevance on a more global scale than, for example, importance maps might tell you. That are more local based often. It assumes concepts are linear half spaces in the embedding space. One disadvantage, I think, it assumes knowledge about the concepts you're probing for. So you need to actually develop this curated data set, which in many cases, you don't even know what you're looking for. Or even if you know what you're looking for, by having this post-hoc approach, you don't know whether the model is really, encapsulating the exact categorization that you have in mind of this concept, kind of hinting towards a topic of faithfulness, unfaithfulness. I don't know if you've had this in the lecture so far. Okay, so just very briefly, faithfulness, it's a very loaded word as well. In the context of explainability, faithfulness often means, is the explanation faithful to the underlying decision process of the model? So is the model really using that, decision process represented via the explanation? Okay, now Rudy told me he has a nice procedure here. I thought it was quite cool. And again, because it was lunch briefly, I thought it might be good to be a little more interactive. This is a little early in the talk, but it's kind of the best point right now before we go into anti-hoc concept explanations. Maybe we'll keep it a little shorter. So please, in small groups, discuss potential questions on the topics you've heard so far. An easy, medium, and difficult question. Maybe we'll take only 2 to 3 minutes on this. So we've discussed very briefly post-hoc concept explanations. Now I want to talk a little bit more about anti-hoc concept explanations, probably because this is much of my research, but also because it's I think it has very cool ideas. Anti-hoc in comparison to post-hoc, I don't know if you've had this, means more by so post-hoc you're trying to understand a model after training. Anti-hoc you're trying to design a model which already has explanations kind of incorporated within it. So another term often used is interpretable by design models. Before I go into some examples of this, what many of these models do, which are so-called anti-hoc, is they combine white box and black box ideas. I know black box is a word you're not supposed to use so much anymore, but we might just call them transparent and opaque models. So transparent models like shallow decision trees, sparse linear models, they are kind of understandable by design. You know what the input, what they're doing. It's a linear transformation. You can kind of follow what it's doing. In comparison, opaque models, they getting the explanations is costly. They are more expressive though. They have a lot more capacity than linear models. So in comparison to transparent models, for example, they support representation, which is very suited for images, but also text. But now, what a lot of so-called concept-based models do is they kind of follow this so-called gray box principle. So they use high capacity, high expressive, opaque model components, but they also use transparent kind of linear model white box components. And the overall idea of this, why you would do this, is that the bottom part, which is usually then the opaque, high expressive model, can support you in terms of doing representation learning. Whereas the top part, the more transparent, possibly linear model, can help you actually interpreting then that part of the before component. So finally, just as an example, you would get maybe in this case, this image shows a fictional character because the kind of the large ears concept or component has quite a high activation, but also green skin, whereas hair is maybe not so important. Now again, to discuss linear models, why are linear models more understandable? Well, if you have a sparse linear model, particularly, let's just focus on sparse for now. If you have a dense one, of course, it's a little bit more complex to understand it, but you can get a pretty intuitive understanding of what a linear model is doing just by looking at the weights. You're multiplying the weights with the input. So if your input is just already, let's say, tabular data, let's say small text snippets, you can say if your weight is positive or bigger than 0, then it correlates with, let's say, votes for the positive class. Whereas if it's negative, it would kind of correlate with, sorry, this is a mistake, correlates with the negative class. Whereas if the weight is approximately 0, it seems quite neutral what this, this input is for the final classification. Now again, linear models, so this seems quite good, but linear models mainly work for linear data or for data which already has this kind of high level representation. For images, as an example, this won't work very well. So we'll focus on first one type of network, so-called self-explaining neural networks, which is a little older for AI terms. But the idea is basically take a nonlinear model, let's say a high capacity neural network, but then ensure that it behaves at least, almost linear at specific points. So the form of this self-explainable neural network is pretty simple to the linear model we've seen previously. The difference is instead of just having, so these are basically weights, so-called relevance scores. But now instead of just multiplying it with your input, you have another model which first maps this to a representation, as a neural network would usually do. yes, that's just the explanation of the individual components. Now, in the end, again, you have a function, potentially a monotonic function, so you can relate back to what the final function is doing to make your final prediction. So in the original paper on this by Barres, Milis et al., they actually use an autoencoder approach. Did you have this? Do you know what autoencoders are? Yes, okay. An autoencoder approach to first learn the so-called embeddings. And then they use another neural network to actually learn the relevances of these embeddings for the final prediction. And then they aggregate these two together to make a class prediction. The training setup is a little bit more tricky than, if you just train a neural network with a classification, because you need to add these additional terms, one for the relevances as well as one for the embedding function. So the first part is just the standard prediction loss, let's say cross entropy. It's quite straightforward. Then the second term is a gradient regularization term, and I'll actually get to this in a little bit more. The idea is it enforces stability by penalizing the difference between the model's overall gradient with respect to the concepts. Again, I think I'll show this on the next slide. Then this term is reconstruction loss. This comes from the autoencoder model decision, basically. Yes. So now this is the second term. Remember, the initial goal was we want a neural network model which is expressive, but still almost linear. So what we do is we actually approximate the derivative of f with respect to the concept vector around a specific data point. What you're trying to do is basically trying to minimize, high divergences in this gradient around this data point. I'll actually, maybe skip a bit of the details here for the sake of time. I do have more details in the slides if you want to look them up afterwards or send me an email. So let me move on to the next idea, which is actually called prototype-based networks. This is actually quite a simple idea. Give me a second. From psychology, which I think is actually quite interesting. The idea is to use prototypes as representations of your concepts. And this is there are these two directions in psychology, one focusing on do humans have this prototype representation in your head versus exemplar representation. Prototype representation would mean, there are many classes of dogs, but when you think of a dog, you usually think of, either a very specific example of a dog, which is more prototypical of that class, or you kind of have this abstract average representation of all the dogs you know. So one idea, because these prototypes are kind of more interpretable, you can present this prototype to someone, they can agree with it. It kind of categorizes your space based on these prototype representations. One idea is now, can we use this idea of prototype representations for building more, transparent models, more interpretable models? And this is where, several papers actually, they focused on this idea. One of the first ones I know of is from 2017. There might be previous ones as well. It's actually quite a simple idea. You again have an embedding function which maps your input to some space. Then you represent each class as one prototype, which basically just means the average over the samples of that class in the embedding space. Now, to distinguish, let's say, a new sample of where it belongs to, which class it belongs to, you just compute the distance in that embedding space from your embedded input sample to the obtained prototype representations. In practice, Euclidean distance works quite well, but of course, there are different distance functions you can use. So then the final probability of an input sample belonging to class Y is then identified as the proportional distance from prototype of that class to the, the distance of the sample to the prototype of that class. And then these prototype representations are actually considered parts of the parameters of this overall model. So it's quite a simple architecture, and it's it's simple, explainable. So again, the probability of one sample belonging to a specific class can be, basically directly mapped back to the distance of that sample to the obtained prototypes. In practice, you can train this model end to end, focusing, both on training the embeddings as well as the final, decision process. I have, again, the learning optimization step. I'm not going to go into too much detail here, but if you start from the cross entropy term, you then focus on the negative log likelihood term. One second. And you derive several steps from this. You get these two terms, which actually can be summarized as the following. So the first part of your optimization term represents the term in which the distance of the prototype to class Y is being computed. The second one is just a soft maximum of the negative distances to other classes. And in doing so, you're kind of minimizing the distance to the true class Y while approximately maximizing the distance to other classes. Yes, there's a question.
When you do this clustering,
yeah,
you might also have clusters that, let's say, there are two lengthy lines in parallel.
Yeah.
And when you choose a representative of the last one, not represented by the center point on the network, and these lines are shifted, then it could be that a member of one of the clusters is closer to the central.
Yeah, certainly. That's a very good point, and I think that's also one of the drawbacks of this model. So you have one prototype per class, and in many cases, this is not going to work well because your classes are probably going to be more complex. The decision boundaries aren't going to be simple Gaussians. This is one visualization of the model on the so-called omniglot data set. Here in the black dots, these are the so-called prototype representations that have been visualized. Now in red, you can see kind of misclassified data samples based on the distances to these prototypes. So I very much agree. This is it's a simple idea. In more complex cases, this might actually be quite difficult. Also in large data settings, this is going to be quite difficult if you just have a few prototypes per class, which basically summarizes the slide. So there are a few more prototype networks. I want to talk about one specific one, which I think is quite cool, so-called proto-P nets, or also proto-part nets, which basically so previously we had one prototype per class, but now, again, so in an image, you have a lot of different things going on. So in images, you also want the ability to identify which part of the image, kind of represents which prototype. So you can answer things like, this looks like that because of, here we see blah, blah, blah. So the idea of proto-P nets is then to be able to focus on parts of the image and then basically do the same prototype idea, but on parts of these images rather than the full image. So you can see quite well here in this bird sample. Let's say you want to classify birds. You might say a bird is this specific species because it has this kind of feather type, this kind of color, this kind of head form, so on and so forth. And that's what you're kind of trying to replicate with this model. So the architecture is quite simple. They focus on CNNs as well, which already give you this idea of, you have patches in your image, you're kind of moving this kernel over your image. And they kind of combine this now with the prototype idea. So instead of the prototypes being the exact dimension of your original latent space in proto-P nets, these prototype representations are smaller. So they only represent parts of the original latent space. The idea is still quite similar to the original proto-net approach. So you try to learn these prototypes during training of the underlying task. And each prototype is still a small latent representation within your model. Now, one crucial point here is that because these latent representations are still uninterpretable, you don't know what they mean. What they do in the proto-P nets, and I'll show you that in a little bit, they actually make sure that these prototype patches correspond to a specific patch in your training set. So that at inference time, when you now ask for the explanation of the model, you get original patches from your training data set as an explanation. So going through the training procedure, again, we have multiple loss terms, which we need to optimize for. The first one, again, is a very simple cross-entropy term. Also here, I have the more details in the slides. I'll skip over that for now. Where was I? Yes. So the first term is a cross-entropy term. The second one is a so-called clustering term. You try to minimize the distance between your input sample to these patches. And the second term is, again, a separability term. You're trying to maximize the distances between the patches. So you don't want prototypes to be too similar to another. So as I said, now in ProtoPNets, what they try to do is to enforce that these prototypes are actually part of your original training set. So they actually find a latent patch in your training set that corresponds best to your kind of latent prototype representation. And then, so after you've trained, you then actually replace the latent prototype representation with that actual training data patch. Now, in the final step, you first only then optimize the final decision layer. Before it was kept fixed in only the kind of the embedding space was learned. So you have this three-step kind of training process with ProtoPNets. So now at inference time, as I said, you map an input image through your network. You get the latent representation. You compare the patches of your latent representation to the patches of the prototype patches, basically. You then identify the most similar prototype. And then finally, you extract the class prediction based on which particular prototype patches have been selected for that image, giving you this overall kind of picture. So again, the key difference to ProtoNets and also other kind of, let's say, full image encoding prototype approaches is that in ProtoPNets, the prototype is a part of a point in the embedding space rather than the entire embedding space. And this gives you pretty cool explanations, or gives a lot more information than it was previously possible, telling you, this image belongs or shows a bird of this and this species, because in this part of the image, I identify a patch which I've seen previously in a data set and which belonged to this and this class. And then you iterate through all these examples. They give you the scores, the similarity scores of each of these parts, finally giving you the decision process. Now, these are quite specific, or these were quite specific kind of architectures. In my experience, the largest amount of work on anti-hoc concept-based models or explanations stem from so-called, usually concept bottleneck models. The form is very similar to what we've seen previously. Basically, the protonets, the self-explainable network, you have one network mapping from the input to some latent space, and you try to make a decision based on that latent space where you add constraints to make sure the latent space is understandable. In simple concept bottleneck models, you just train a let's say concept extraction module, typically a neural network again, to predict concept annotations of your input image. So this is actually more of a supervised case. You already have annotations. You train a model to predict the annotations. Then you have a second model, which makes the prediction based only on the activations of these concept predictions. And this is actually quite important. There are different ways of training these. You can train the whole thing jointly. You can train them kind of iteratively, or you can train them really separately. So you train this part, then you leave it, and then you train this part. In practice, it's kind of been shown that if you train them jointly, you can have a lot of leakage between the concepts, such that basically the explanation is unfaithful again, because you have information about, let's say, the beak length, which is also in the undertail color. So what you want to do is you want to train them really separately. Anything else? Yeah. So by training separately, particularly, your model's final decision process is roughly independent of the input given these concept activations. And one, I think, very important finding on this is that Ko et al. In 2020, I think, 20, thank you, showed that given good concept, annotations or representations, these kind of models can be just as good as large opaque models, which I think is pretty important. And I'll get to a point on this in a few slides. Now, some more advantages of these architectures or this kind of procedure is that it allows for different forms of interactions between human users and these models. One which they showed in the original paper is that you can actually perform interventions now on this concept activation. Now, let's say your concept extractor has made some mistake and has mispredicted the color of the wing. If you as a human user have identified this, you can correct the final decision process if it's been focusing on the mispredicted concept activation by just intervening on this concept activation, saying actually, this should be 0 or 1. And in that way, you can influence the model to be right for the right reasons. I have some more slides on this. Was there a quick question?
The size of the models is explicitly mentioned. So are these kinds of models performing even when they're smaller on par with larger models?
I can't say specifically, but I think they compare it to an equally expressive model in the original paper. Of course, I don't think there's a guarantee. If you have a very weak model here, which does a lot of mistakes, then of course you're going to have issues downstream as well. So I don't think there's a general rule on this. I guess so. The main point was, if it goes well, it can be as good as the opaque model. Now, of course, the question is, how does it go well, or when does it go well?
But yeah, I have another question. So this seems to work well, like if you have, like in this case, for instance, these visual concepts, right? Like so that there's like the beak length and these kind of things, right? But let's imagine like you want to classify something that actually depends on object relations. So for instance, you have a plate and then you have like the cutlery next to it or the cutlery on top of it, right? So the concepts of cutlery and like plate will be there, but those are significantly different things. So
Yeah.
I can imagine because these relations are continuous, right? This discretization in concepts will become fairly difficult. So how do you do you know if, or are there approaches that actually tackle that issue?
So that's a fair point. Let's say the hierarchy here is very simple. These are, again, or if we go back to one of the first slides, the logic of this is very simple. We're saying the image has this property. Now, particularly in visual settings, also in robotics settings, where you're interacting with the world consists of objects, you need a lot more fine-grained concept representations or hierarchies of these. You need to know which object has which property, what relation are these objects to another. And we discuss parts of these things in the next slides, but it's an ongoing research. And so we just, for example, submitted a work on having these models more object-centric, so focusing really on the object properties. The next step would be, integrating relationship not relationship, relational information into that bottleneck as well.
Thanks.
Yes, so we discussed about interventions. Now, going back to the original idea, how can we use explanations to mitigate shortcut behavior? Having this explicit concept information can help you very much also in fixing these models. How do we do this? It's actually quite simple. Don't worry about the architecture. It's a little bit more complex, but the idea is the same thing. We actually now break up the image into object representations, have the concepts per object. Now, if we get a prediction, we can get the following explanation from the model. One, on the concept level, telling us which concept is relevant for the prediction, but then also telling us which objects or which part of the image belong to these concepts we've seen. So now, similar to the explanatory interactive learning approach, we can give feedback. But in this setting, which is, I think, pretty cool, we can give very much more high-level global feedback, saying like, I don't care, what it is for individual samples. For all the images, you should never focus on the color gray. What you do is you then transform this logical feedback again into these simple feedback masks, and then you can use the same regularization terms that we'd seen previously. And in this way, you can get the model to be right for the right conceptual reasons, or often also called neurosymbolic reasons. This is not so important for now, but basically we're showing if you do this, you can improve your model's performance on a confounded test set much higher than if you have just a CNN approach with the original input level explanations as feedback. So to summarize what we've had in this next section, so anti-hoc approaches, they are a little bit more, or actually a little more specific to implement than the post-hoc approaches. It has a big advantage that the extracted concepts or the representations of these are a lot more faithful because the model's actually using these representations to make a decision. We've seen some approaches which require concept annotation, which of course is a drawback. You need to know again in advance what you're looking for. I'll get to a bit in the next slide on how we can mitigate this part. Yes, where some approaches, however, have focused on, okay, we don't know what concepts we're looking for, let's try to learn them via the downstream task as well. And we've seen, finally, that having these explicit concept representations, we can perform a lot more, interventions, feedback with these models, try to fix them or debug them if they're doing something wrong, but on these high-level concept representations. So that's so much to that part. I think it might have been a bit much, but now is the next question break.
Hey.
Yeah. So we've seen in a few cases either the concept information is provided upfront as annotations, or they're kind of they're known upfront. In some cases, they try to be learned via the downstream task, and this is kind of related to the next topic on actually how do you learn these concepts in general, particularly if you don't actually know what you're looking for. So there are quite a few works now on this. I'll be actually focusing a little bit on our stuff on this. Why is it difficult to learn concepts unsupervisedly, particularly in the visual world or in the visual domain? So the visual data is object-centric. So basically you want concepts to be related to objects. Then there's a big discussion on, concept representations at all. Should these be continuous representations or should these be discrete representations? If you want continuous representations, these are much more easy to learn via standard optimization. If you use discrete ones, they're tricky to learn. You might be stuck in local optima. However, discrete representations are easier to understand. You can inspect them. They're kind of categorizing something, whereas continuous ones are more difficult to understand. And tied to this, discrete representations are much more easy to revise because you can just manipulate the symbols rather than having a continuous representation. Yes, a question?
Have there been approaches that try to mix all?
Exactly, that's what we're going into.
Okay.
So this is one approach we published last year, the Neural Concept Binder, which tries to do this. So unsupervised visual concept learning. It focuses on utilizing object factor disentanglement approaches, then basically just does a clustering on these factors and uses a retrieval-based approach at inference time. So the idea is exactly this. We actually combine both continuous concept representation learning with discrete concept representation learning. I'll go through this. I hope most of it is understandable. There might be a few things here which are kind of new, but we start with a encoder-decoder architecture where the important thing is instead of just having one big image encoding, which you usually have in like autoencoders or variation autoencoders, whatever, you have a structured latent space which maps your input both to objects or object encodings as well as so-called factor encodings. These factor encodings are blocks within your object encoding space, which ideally should represent specific factor information of your objects. There's no guarantee for this, but in practice, it seems to work quite well. Now, the idea of NCB is pretty simple. Once you have this structured latent space, you just do a clustering, not on the full image encoding, but on each individual block encoding. So you're trying to cluster these, these factor encodings. You then distill the result of this clustering into a so-called retrieval corpus, which is basically a dictionary of encodings. And we take two specific encodings for this, and that is related to the previous question. We use cluster means, so basically prototypes of each cluster, which are, you don't see it, but there are these stars here in each cluster. And we use exemplar encodings as well, which provide a lot more kind of robustness to represent the individual cluster. These exemplar means are then are encodings, sorry, not exemplar means. These exemplar encodings are encodings of actual training samples, which we've seen. So we put the encodings into a retrieval corpus. We basically tie the cluster ID of each of these clusters to the individual encodings. Now, these cluster IDs are basically our symbols. They don't have a meaning yet, but they are symbolic and categorical in the sense that if we have an encoding, we know, okay, this belongs to A1, whatever that means so far. Now, at inference time, what you do is you pass an image again through your encoder, which gives you the structured latent space. Now, per object and per block, you look up in your retrieval corpus which is the closest encoding I have for this block, and I extract the basically the symbolic value or the cluster ID corresponding to that encoding, and by doing so one by one, build up so-called concept slot encodings. So this is a discrete representation per object, giving us basically numbers. So in essence, we have a continuous encoding, which is structured, and we just extract from this continuous encoding by hierarchical clustering specific IDs, which we can then use downstream. Now, the big question is, how do we actually map information to these IDs? Because these are just, random numbers. The specific framework we introduce here allows to very easily kind of inspect and investigate these individual concept encodings or these symbolic encodings. Because what you can do is you can visualize by decoding again. Actually, I'll have a slide on this. Yeah. So what you can do is you can visualize the actual objects which have specific symbolic values, but you can also kind of play around with these decoded images. You can replace encodings in the object encoding. Decode the image, get out a different image, and compare them. You can ask so-called interventional questions saying, okay, if I have this object, but now I use a different prototype rather than the one I've seen previously, how does this influence the object? Yes. And the training approach is also pretty simple. So in comparison to all the previous, particularly anti-hoc approaches, which had multiple loss functions, we actually just have one loss function, which is the reconstruction loss. Then we basically just do a clustering on the block encodings and distill the information from the clustering into a retrieval corpus. That's basically it. So because we are introducing a huge bottleneck in the end, we would just have discrete representations versus the continuous ones. So if you want to compare numbers, previously at the beginning, we have, I think, 2048 continuous variables. In the end, after this discretization step, we might just have a few hundred discrete variables. But we show that by combining these two approaches, so first continuous learning and then discretization, you actually get a concept space which is almost as expressive as the original continuous one. So there's not much loss of information. So what you actually see here is that if you train a linear, so basically we're doing probing here again, if you train a linear classifier on these embedding spaces again to predict, let's say, ground truth concepts you know of, there's, and then we're showing the accuracy of that classification here. There's a question.
Yeah. How do you deal with clusters of different sizes, and how do you deal with how do you get the number of elements for each cluster?
So that's why we use hierarchical clustering. So there's a specific clustering technique, HDB scan, where you don't have to provide the number of clusters you're looking for. So basically, you can heuristically decide. So what it's doing, it's basically building a tree of distances between encoding objects, samples, whatever. And then you can kind of decide on where you want to cut the tree. And where you cut the tree, that influences your final clustering. And there's specific heuristics you can use on where's the best part to cut the tree. And that's how you do the clustering. And sorry, the other question was different sizes? No.
Yeah, the first thing would be different sizes, so if you have clusters with different spread. And the second part of that question would be, what if you have clusters? One cluster, you have 1 million examples, another cluster, you only have 100 examples, but let's say the cluster with 100 examples still has a lot more entropy, so you might need more representatives of that cluster to truly be able to classify it correctly, while with the one with 1 million examples, you wouldn't really.
Yeah, it's a good question. So the clustering method itself also provides a means to extract exemplar, basically samples from the clustering. I have to admit, I don't know if it allows varying the number of exemplars it gets out. That might be something worth looking into. But so in these data sets, it wasn't an issue. Who knows in more complex ones? Yes. Yes.
We had, I think, earlier today or yesterday, an example of the Swiss cake roll in 3D.
A Swiss
cake roll.
Okay.
A stretched spiral. And that could possibly be one cluster. And if you, for example, now had a cluster in the middle of that was not connected to the spiral, you might still, with the hierarchical clustering and traditional distance measures, end up with a cluster that incorporates elements from two different classes.
Sure. So I guess your point is the clustering is not going to be perfect, and that's so. There are many parts in this that are not, there are no guarantees for it. We don't have a guarantee that actually each block represents one factor. We don't have a guarantee that each slot represents an object. We don't have a guarantee that the clustering here will be perfect. That's why we put a lot of focus on, particularly if you do unsupervised concept learning, you want the human in the loop, at least to kind of evaluate what the model has finally learned, because the model's learning unsupervised things. So if, in this case, your clustering has gone very wrong, and you're actually clustering, let's see, I think I have an example. Let's just say it's done something weird here. It's kind of put it's created two clusters of the color purple, which you as a human would say actually just belongs to one. You don't know if there's something really underlying here. Maybe actually the images or the objects of this class are slightly different. Who knows? But what you can do is you can now just update your corpus space by just saying, okay, actually this cluster doesn't exist. I want it to merge with all the other clusters.
But couldn't you merge clusters into the surface? So you do it bottom up, you have very small clusters, and instead of saying each two elements in one cluster need to be close together, they just need to be connected by close points.
Sure, that's something one could look into. Okay, let's move on for the sake of time. So what we've looked at so far is how to learn kind of so-called basic object-centric concepts. So these are concepts, properties tied to one object. Now we already had a question, what about relations? Which is very important because also in the visual world, objects are in relation to another. What we looked at here is now, can we learn relational concepts from the visual world. And what we did was we focused on actually creating program representations of these relational concepts. And we did so by utilizing the idea of program synthesis. So I don't know if people know about this, but it's basically a model is given a set of basically examples which show a task. In this case, the underlying task is to sum the numbers in these lists, and the output should be the sum of those numbers. Program synthesis now tries to find a program which basically describes the behavior that it sees in these input samples. And we want to use this in the visual world. Now, again, this is a big graphic, but it's quite simple. We first, again, extract from the images specific properties. In this case, we focus on supervised because we're focusing here on the unsupervised program synthesis approach. Once we have these basically discrete object properties, we then pass it into the so-called program synthesis module. Now, this consists of a code model, which is actually a neural network, which does a search over possible, basically, program snippets and how to combine them to get a program which best describes the input samples. We are providing a few base primitives up front of like basically logical things it can do, or the logical primitives, but the whole program synthesis approach actually learns to abstract bigger and bigger primitives, which it can then use to recombine to make bigger concepts. And by doing so, you kind of get this library of program concepts, which are kind of interconnected to another. So one concept or one program might actually be using a kind of lower level concept to find its final prediction. And so in this case, this is focusing more on these list-based approaches or these kind of list-based input. Here are these example programs coming out of if you actually put in images. And this actually works quite well also on not just these simple synthetic images, but also on these natural images. Okay. So those were just an excursion on how to actually do unsupervised concept learning, but in a way that we can inspect these concepts and maybe actually also revise them. Now, we had talked about concept bottlenecks previously, and the models I was showing were somewhat older, again, from the AI perspective, 5 years old. One major drawback of the concept bottleneck models was that they're using supervised concept annotation to train the bottom part of the model. A lot of works now are actually using kind of the advantage of generative or of large scale models to guide that approach. So you don't need so much information up front of what you're looking for. The classical setting would be you're kind of just asking or probing a LM, a VLM for what are the concepts you see in these images. You then use that to basically build your concept bottleneck model. Most of the approaches, I have to say, they all use CLIP because the CLIP has this vision language grounding idea. It doesn't work so well all the time, but still you can use it to some degree to get visual embeddings of an image, but also get text embeddings, which you can then compare to identify what are basically the textual concepts which are within an image. And the idea of this is reduce the annotation burden. So in many cases where you don't know, or you just have a lot of data, you need to annotate up front. You can reduce it by using these pre-trained models. You can, to some degree, enhance generalizability because these models have been trained on huge amounts of different data. If you were to annotate yourself up front, you would have to do this again for each domain differently, probably. And then the idea in this setting is usually to use language as a means of representing your concept representations. And in this way, kind of improve the interpretability. How are we on the time?
I mean, you have officially 8 minutes, but basically need 10 or 15.
Okay, I'll just skip this part a little bit. So this is one idea we had recently to use these pre-trained models also on the object level. So we actually get object encoding or object concept encodings. So you can use a SAM or even previous models, RCNNs, to first get object proposals. You then use CLIP, for example, or the approaches we've seen previously, to identify specifically for these object annotations, what are the concepts, and then you combine the overall image level concept encodings with the individual object encodings. And by doing so, you get a much more rich kind of description of your image in this concept space. So just as an example of how you can use these pre-trained models and the power of them, the pre-trained models themselves, of course, are tricky, but I think there's a lot of potential in using them. Now, finally, I thought I have to talk about this. I don't do much research yet on this, but all of the approaches we've seen so far have been on quite small models, quite specific ones. Of course, all the new kids today, they use LLMs and VLMs, which are huge models we don't understand. Most companies are fine with that, but some people like to understand what are these models actually doing. And one idea here is to use so-called sparse autoencoders. Now, sparse autoencoders, if you don't know of them, are basically so the autoencoders, but instead of trying to compress the latent space by, let's say, constraining the size of your latent space, you're actually increasing the latent space to a ridiculous amount, but you're adding sparsity constraints on this. The idea particularly now for large models is that, let's say your original encoding space is entangled and you have information in it. The hope is by increasing, like really blowing up the autoencoder's latent space, you might be able to identify you might be able to disentangle the individual features which were entangled in the transformer's latent space.
But is it really sufficient to only have sparsity in there? Because if I add, for instance, like a sparsity constraint, like L1 norm, whatever, right, on a spank, then there's nothing in itself that prevents this from still just choosing a lower dimensional subspace of this large space.
Sure,
then you have like a de facto autoencoder again, right?
Yeah.
So you need to somehow also ensure that there's actually diversity in the space.
Yeah.
So how do you do that?
That's what most models add an additional term for them. So they actually try to add this diversity across your latent space to make sure you're not just using a small set, but actually the full.
Okay.
Yeah. Is anything important here? Maybe I'll just skip to this. So again, the general idea is you add a sparse autoencoder to specific parts of your network. There's actually different work on this. So, I mean, because there are many different layers in LLM or VLM, depending on where you add your sparse autoencoder, you're going to get different concepts. I don't know if you remember from your lectures on CNNs, the idea is also in the brain. You first have very general kind of features you're detecting, maybe lines, corners, that kind of stuff. The further you go down the CNN, the more complex features you're encoding. A similar idea kind of applies here. You have to kind of, there's no golden rule on where to apply the SAE. The structure is very simple. You basically have one encoder with a nonlinearity, then you have one decoder, and you're trying to add a sparsity term, as we said, also potentially different terms to increase its diversity. And there's a lot of promise in the SAEs, but there's also a lot of limitations, which has also come out recently. So first off, there is this kind of reconstruction sparsity trade-off. So you're trying to have a good SAE, which learns a good encoding, which can reconstruct the original transformers encodings, but you still want it to be sparse and diverse. Then there's the scalability issue. I mean, these transformer embeddings are already pretty big. If you're trying to learn a much more blown up latent space, this is not cheap. So it comes with a cost. Then similar as with NCB or the other approaches, there's no guarantee for this disentanglement. There is this idea of the linear separability hypothesis, but just by blowing up your space, you're not guaranteeing that semantic information is being routed to only one specific neuron. Then additionally, I mean, if you have this huge latent space, somebody has to actually interpret what this latent space now means. I mean, sure, maybe this is more monosemantic than previously, but you still need to look at it. And again, there's this topic of faithfulness, and I'll come to this in a bit. You're training an additional model on a model. So there is still this ambiguity of whether what the second model has learned is actually what the first model has, learned. This is kind of one of the classic examples with which at least I became aware of it. I think many people became aware of it from Anthropic, showing that specific neurons within this autoencoder latent space seems to prefer or fire at Golden Gate mentions. Now, where do SAEs belong in this, let's say, categorization of anti-hoc and post-hoc? I personally am not so sure yet myself. It's because the SAE's goal is different. But let's just go through it. So they're not strictly anti-hoc because, again, this is not trained within the first model to make sure that the first model incorporates this. But so it is post-hoc to the sense that the SAEs are trained after an initial model has been trained. But the main goal of SAEs, not always, but most of the people using SAEs, they're not trying to get an explicit explanation from a model. They're just trying to understand what is in the model. And I think that's it's a slight distinction, but I think it's quite important to make. So SAEs, I consider, are just a powerful tool to do kind of reverse engineering of a model. They don't give you an explanation directly. Related to the previous idea of concept learning, which I think is also quite strong in this relation, you could say SAEs are trying to uncover the concepts in the original model, same as we had seen previously. The main difference is, I think, again, the SAEs are a post-hoc approach for this. In NCB or Pix2Co, we've seen the idea is you build this concept space and then you use it downstream. So you're sure the model's actually using it. What we actually see in quite a few SAEs approaches, once you've learned the concept and you're trying to kind of intervene on the original model, for example, by steering on these concepts, it doesn't actually work that well, suggesting that the model has learned something, the SAE, which you can't really use on the first model. And then, the key mechanism differences in the NCB specifically, we're trying to learn this hierarchical clustering, whereas in SAEs, we're adding this, just huge space with an additional sparsity term. One thing so this is kind of the final slide I'd like to talk about or just mention, is this idea of using automatic interpretability agents. So again, maybe use these models so we can interpret other models. And the idea is quite simple. You're basically giving an agent, some kind of VLM, LLM, these tools to analyze a model, similar as you would a human. And the agent would now basically build a protocol to kind of test the original model. So let's say you provide code to an LLM to perform, let's say, image manipulations or to intervene on specific neurons in the model. And by doing so, the LLM can kind of create a report about the original model. I think it's an interesting idea. Of course, you're kind of, having an LLM kind of test another LLM. There might be some issues there. You might want to be careful, but I think it might be a promising approach to particularly investigate this huge space of, for example, SAE neurons that are coming out. So finally, what do I want you to take away today? I think it was quite a bit of information. Again, it was my first lecture. Hope it was okay. But for me personally, I think concepts represent very important building blocks also in human logical communication, but also thinking. And I think we need these concept-based explanations, A, to understand the model, but B, to make sure they're doing the right thing. So to debug them, for example. Now, the topic of faithfulness is a very important one. You can learn concepts from a model, but if you're not certain the model's actually using those concepts, there's not much benefit in terms of making sure they're doing the right thing. One tricky thing, so anti-hoc models are often kind of being called as, they're simple models. It's quite a nice idea, but doesn't scale to big approaches. I agree to some degree. I think more research needs to be done in that context, but I think it's still open whether you can use these also in much bigger scales. Now, finally, this obtaining and learning understandable concepts, it's a tricky topic. I mean, it's quite underspecified anyway. And I think there's still a lot of work that can be done there. So that's that. Now, I don't think we need a question break. I think the lecture is over, but if there are any questions, feel free to ask. Yes.
Earlier it was mentioned that you want to have diversity in the roll-up as far as basis. If you introduce a new loss term there, how would that look? Would you try to increase the entropy of this sparse representation within one batch, or how would you train that?
So I'm not an expert on this. I'd have to refer to the literature there. That I'm certain that could be one approach. I think one approach is also just making sure that basically the activation of the neurons is uniform across your training set. But don't pin me down on that.
Well, if you actually manage to represent latent space somehow like that, or if you consider it as a mixture of Gaussians, right? If you maximize the entropy of a mixture of Gaussians, that is equivalent to pushing away the clusters from each other. So that would exactly achieve what you're trying to do. So that's why, like, and again, you can use for instance, like negative K divergence or like some stuff like that, and or some measures, anti-measures like that to push it out.
But you would do that within one batch.
I mean, usually you have to approximate it in one batch, right?
Yeah, like, I mean, you would do it for every batch.
Yeah.
Right, like you would do this like every time you get it, like, and you do this on your latent classes. But yes, it ends up being part of your loss period. Okay, yeah.
Another question.
Do you want constructive criticism on the first lecture?
Yes.
Is there recording stuff?
Let's. I mean, are there any?
Wait.